Get seated. The last session is starting, last session of the day. For this session, we are continuing with the galaxy cluster theme that has been started by Chunhao To from the last session. And our first talk is invited. It will be given by Tomomi Tsunayama all the way from Taiwan. So.
Thank you. So today I will talk about optical cluster cosmology with current and future galaxy surveys. So how can we use like cluster as a cosmological probe, which is actually pretty simple, that we can just count the number of clusters. So here I'm showing two n-body simulations with and without dark energy. And by eyes, you can see the number of massive objects are very different. This is because, and the reason we can use cluster as a cosmological probe is because Taylor halo mass function is sensitive to cosmological parameters. Another word, when we measure the halo mass function, when you vary omega matter, it changes the overall amplitude, while when you change the sigma 8, it changes the number of massive halos. So by using cluster as a cosmological probe, we can constrain omega matter and sigma 8. So according to the Cosmic Vision Report 2016, the number of massive galaxy clusters could emerge as the most powerful cosmological probes. So here I'm showing the statistical precision that clusters can achieve for stage 3 and stage 4 experiments. And those 4 black lines are the precision that the cluster in general can achieve. And the reason that there are 4 different black lines is because the precision that the cluster can constrain cosmological parameter really depends on how low mass you can actually find clusters. So if you can actually detect like 10 to the 14 solar mass clusters, you achieve this bottom black solid lines, which means that for certain redshift range, actually optical cluster or clusters in general can do better than like stage 4 experiment combining CMB, weak lensing, BAO, and supernovae. However, this premise for cluster cosmology actually has a if statement, which is that if the mass of the cluster can be accurately measured, this is because cluster mass is not direct observables. What it means is that in theory, what we can predict is a halo mass function, which is sensitive to omega matter and sigma 8. So it's a number of clusters as a function of the halo mass. While what we can actually observe, number of clusters as a function of observable, and this observable depends on what kind of data set you use. For the case of optical clusters, we call like richness, which is basically the sum of the member galaxies in the cluster. And in order to infer this halo mass function, you need to assume some kind of mass observable relationship. And among many different ways to identify clusters, optical clusters are known to be susceptible to many systematics. So why do we want to do like cluster cosmology with optical clusters? One advantage for optical cluster is that we can actually identify lower mass clusters compared to SZ and X-ray clusters. And if we have more number of clusters, which means that we can do better weak lensing mass measurement and better constraining power on cosmological parameters. So here on the left, I'm showing the limited mass that different surveys can go to. So the yellow and red, the dashed line are from the optical, like from DES and LST, and green is from X-ray, and purple and blue is for the CMB SZ clusters. So as you can see, that optical clusters can be identified roughly like 10 to the 14 solar mass all the way up to redshift 1.1. And if you translate how many number of clusters we can identify, this is shown in the right figure. So optical cluster cosmology is pretty simple. From the theoretical side, you set the cosmological parameter, you get like halo mass function. From the measurement side, you find clusters and you count the number of clusters. And you relate halo mass function and the cluster abundance using mass richness relation, which is often calibrated using the weak lensing. And then this was a result from the DESY1 in 2020. So the gray contour is from the DS optical cluster constraints, and as you can see by eyes, DESY1 cluster constraints are not really agreeing with any other cosmological probe from CMB, other cluster probes, which is in the purple and yellow, and also DS 3x2. Especially the disagreement between DS 3x2 and DS clusters, which share the same data set, which are highly correlated, kind of makes people in the community think that can we actually use optical cluster as a cosmological probe? So one of the major systematics for optical cluster is so-called projection effect, which is the misidentification of the member galaxies along the line of sight. This happens because when we identify clusters from the photometric data set, what we are using is an image of the galaxies. So along the line of sight, distance uncertainty is large. So this alters the mass richness relation. So what I did was investigate this projection effect by constructing the cluster mock catalogs with and without the projection effect. So basically, for the case of the cluster without the projection effect, I just count the number of galaxies in the mock halos, while for the clusters with projection effect, I grouped all the galaxies within the cylinder with certain lengths, which I set to 60 megaparsec for this case. And I compare the mass richness relation. So the solid line is the mass richness relation for the clusters without the projection effect. And dashed line is with projection effect. And as you can see by eyes, projection effect basically broadens the mass richness, the mass distribution for each cluster samples. So including this projection effect in the mass richness relation, is this the end of the story? It's actually not, because when we calibrate the mass richness relation using weak lensing mass, we usually assume statistical isotropy in the cluster detection. But we never know how the projection effect actually affects the weak lensing. So what I did was measuring the cluster lensing from two different directions, although like keeping the projection effect along the z-axis. And by measuring the lensing signal from two different directions, here I'm showing the lensing signal measured from this direction in the numerator, and also comparing to the lensing signal measuring from different angles. And what I found is that on the one halo term, there's no, the lensing measurement from two directions are actually agreeing, meaning that the statistical isotropy is kept on the one halo term, while on the large scale, you see that the boost on the amplitude. What this means is that the distribution of the optical cluster is actually anisotropic, which makes this boost on the large scale. So if you don't include this boost effect in the cluster mass measurement, your inferred cluster mass can be biased. So this is one way to model the projection effect using some nuisance parameters. So here, the lensing signal, sigma of R, shown in blue is with the projection effect, and the orange line is without the projection effect. And the green line is the difference between those two lensing signals. So basically using those three parameters, we could model this boost effect in the lensing signal. And then using this model, instead of doing like comparison of the halo mass function and abundance using mass richness relation, we can also do the cluster cosmology with the full-forward modeling, meaning that from the measurement side, we find the clusters and can measure cluster abundance, lensing, and cluster clustering. And from the modeling side, we can do the same. And one of the advantages of doing this method is that instead of just inferring the cluster mass from the cluster lensing, small scale like 1 halo term, we can infer the mass richness relation. But from the large scale, we also have the information of the cluster bias, which is a function of the cluster mass. So by having the cluster lensing and cluster clustering on large scale, we have some additional information of the cluster mass from the cluster bias. So, and including projection effect is important. So here, I'm showing the cosmology constraint with and without projection modeling. And as you can see by eyes, when you don't include the projection effect, it's biased in omega matter to lower omega matter and higher sigma 8, which is somewhat consistent with DSY1 result. So including the projection effect in the optical cluster cosmology is very crucial. And we actually applied this model and analysis pipeline to Sloan red mapper cluster sample together with HSC Y3 lensing measurement. And we get the consistent result between cluster cosmology and other like weak lensing analysis. So in the left, what I'm showing is, so this blue contour is a result from red mapper cluster together with HSC Y3 lensing measurement. And another contours are from the HSC EF3, 3x2 or cosmic shear. And this small yellow line is from Planck CMB. So with my analysis, I didn't see any tension between CMB and cluster cosmology constraints. And also in the right, I'm comparing the cosmology constraints from different cluster analysis from EFES, DS, SPT, and SZ. And all those cosmology constraints are consistent within 1 sigma. So now for HSC, we have completed the survey, and now people are working on the final year catalog. And one of the things for optical cluster cosmology is that instead of using SDS red mapper clusters, now we want to do like more tomographic analysis, because using HSC data, we can actually identify clusters at higher redshift. So here I'm showing the number of clusters as a function of the redshift up to redshift 1. And by using the redshift evolution of the halo mass function, we can constrain the omega matter much better. And how about for the cluster cosmology with Hubble Space Telescope? So I can think like 3 directions. One is that the complementarity to LSST DESI cluster cosmology by doing the cluster lensing measurement using Raman data. Another science case is a synergy with Raman grism survey. And the last one is high redshift optical cluster cosmology with Raman data. So this is a timeline of the photometric survey in the stage 3 and stage 4 experiments. So this year, Rubin LSST just like started to take data. And one of the complementarity between Rubin and Raman and LSST is that different number of source galaxies, meaning that by using the Raman Space Telescope data, you can do like more precise like lensing measurement for clusters. So this is a forecast conducted by Heidi Wu in 2020 as a function of the area and the number of source galaxies. So Rubin LSST can achieve the precision of sigma 8 of sub% level. For Raman, because of the area, the precision on the sigma 8 is not comparable to LSST. However, if you actually think about the weak lensing measurement constraints, it can be comparable because the number of lens source pair can be almost the same. Another complementarity is that synergetic science case with Roman Grism survey. So either assigning the spectroscopic redshift to the cluster optical clusters or doing the cross correlation of the optical cluster and spectroscopic redshift, we can measure the 3D clustering. And with the 3D clustering, the additional information what we can gain is baryon acoustic oscillation and redshift space distortions. And from the baryon acoustic oscillations, by combining the cluster, you can really constrain the omega matter more precisely compared to when you combine the cluster abundance and lensing, which is so the result of combining all like number count, lensing, and cluster is shown in red, while the number count and lensing is shown in the blue line. Another information is coming from the redshift space distortions. So by combining the redshift space distortions, you can also constrain omega matter and sigma 8 more precisely. So for this case, by adding like redshift space distortions, omega matter and sigma 8 can be improved like 60% and 40% respectively. And the last science case that I was thinking was high redshift optical cluster cosmology with Raman. So in this figure, LSST and DS only goes roughly redshift 1 because they're using like red sequence cluster finder, and those are the redshift range that LSST and DS can find red sequence galaxies. But with Raman, having like different wavelengths, you can actually find red sequence galaxies at higher redshift. So the question is that, can Raman find lower mass clusters and SD clusters at redshift greater than 1.2? If we cannot find like, if we only find similar number of clusters compared to SD, I think there's no reason to do like optical cluster cosmology because they're more systematics for optical clusters. However, if we can actually find much more number of optical clusters at higher redshift, I think there is some like complementarity to do cluster cosmology with optical and SD. So the challenges for high redshift cluster cosmology is one is that the number of clusters decreases as going to higher redshifts. There are not many like massive objects. Another challenge is that member galaxies in the high redshift cluster do not need to be red. So another question is that, do we want to use red sequence cluster finder, or do we want to do some kind of different way to identify clusters? So actually, we cannot really use red sequence galaxy cluster finder for Raman optical cluster cosmology because many of the member galaxies in clusters are actually not red. But so instead, we need to use photometric redshift to identify optical clusters. But if we use all the photometric galaxies identified in the Raman data, the current forecast is that we can actually find roughly 10,000 clusters at redshift 2 with mean mass of the 10 to 13.5 solar mass, which means that we can actually find much more number of clusters than SD clusters. So there is some complementarity to do the cluster cosmology using optical clusters. And I will leave my summary, and thank you for listening.
Thank you very much for a very nice talk. We do have some time for questions. Now, before you ask questions, it would be really nice if you can briefly introduce yourself, your name and institution. Yes.
I'm Kustra from Leiden University. So you talked about lensing the mass, so that's fine, but you didn't really talk about the mass function. So because you showed that also because of baryon feedback, the halo mass function is changed, which leads to bias. For your analysis, did you use a hydro mass function or was it dark matter only?
This is only dark matter. But so for the HAC, like SDSS and HAC analysis, our statistical precision is not really there yet. So I agree that baryonic effect can bias the halo mass function, but it was within the statistical error.
But so going forward, would you think that's a concern also?
For LSST disk, yes. For Roman cluster cosmology, because the area is so much smaller, I don't have the exact error, but I'm not so afraid of the baryonic effect.
Any other questions?
We have one online.
Oh, great.
Question from Dutta. He says, what does it mean distribution of the cluster is anisotropic?
So what it means is that due to the cluster finder, due to the way optical cluster finder works, that cluster finder tend to identify low mass object on the filament which are aligned along the line of sight compared to the filament which are perpendicular. So there is a preferential selection of aligned structure rather than the perpendicular, which makes the distribution of the cluster anisotropic. Yeah.
Another question there.
Hi, Eva Malcheva, MPI. What are the prospects of merging points 2 and 3? Can you use the grism spectroscopy to identify more high-redshift clusters?
So Roman grism survey definitely helps to make the completeness and purity of the cluster sample better. But because the average number of member galaxies which will have spectroscopic redshift from the grism survey is pretty low, like 2 to 3. So it's kind of hard to just use grism data to find the cluster, but it definitely helps.
So if I may quickly ask a question. So you talked about the importance of projection effect, which is, we see how much effect it has. Is it for your model, is it mass dependent, the projection effect?
So from the simulation, okay, so it's not mass dependent, it's more richness dependent because low richness tend to be highly affected by the projection effect. So the fraction of the contaminated clusters or more contributing as an isotropic cluster sample, it becomes higher, going to lower richness.
Okay, makes a lot of sense. Any other questions in the room? Oh.
Maybe one final one, because you talk about these orientations. Have you looked at sort of the distribution of satellites or even the BCG? Because people have found that actually some of the scatter is reduced when you look at the BCG and the lensing system.
Do you mean
the shape of the BCG?
So do you mean looking at the shape of the BCG as a tracer of the orientation? So actually, sorry. So it's true that actually more oriented, elongated BCGs are selected for optical clusters, but actually it doesn't really contribute to the lensing signal, at least from the mocks that I use. So as you can see on the one halo term, the agreement between looking at lensing signal from different directions were almost one, means that there's no significant effect due to the orientation of the BCG on lensing.
But I think it's been seen in data.
Yes, there are some fraction of oriented, there are more oriented BCGs in the sample, but statistically it doesn't really affect. Yeah.
So thank you for the very nice discussion. Unfortunately, we do have to move on to the next talk, but thank you again. Great, thank you. So our next speaker is going to be Kaifeng Chen, who is a PhD student at MIT.
Okay, thank you everyone. My name is Kaifeng Chen. I'm a student at MIT. And today I want to talk about a relatively new avenue for cluster cosmologies that is only possible thanks to deep and wide lensing surveys such as Romans. This is by choosing galaxy clusters directly from weak lensing maps and use them to constrain cosmologies. And I'll demonstrate the possibility of these using the super HAC data. This is in collaboration with the HAC weak lensing working group, in particular with Tomo at Taiwan and Masamune Oguri in Japan. So, as we hear from Tomomi, galaxy clusters are excellent probes for cosmologies because simply by counting the number of halos as a function of mass and redshift, you get sensitivity to the underlying cosmological features through the halo mass functions and also through the sensitivity to the geometry of our universe. However, one of the main challenges for cluster cosmology, one of the main challenges for cluster cosmology is to quantify the observable mass relationship between, because the cluster mass itself is usually not the direct observables. What you usually observe is looking at the clusters in either optical, X-ray, or radio, and you're looking at these observables that are tracing the underlying baryonic content of the halos. And you want to connect that to the underlying dark matter halo mass, which you usually quantify through some scaling relationships, which you need to then calibrate. And also, the selection effect also depends on these complicated baryonic physics. So typically, weak lensing data comes into play traditionally by doing a mass calibrations to calibrate these scaling relationships. However, because of the uncertainties in these baryonic physics, sometimes your cosmological constraints are limited by your uncertainties in not knowing the underlying baryonic physics. So what we want to do is whether it is possible to directly do cluster cosmology using weak lensing data alone. This is by making weak lensing maps, like on the far right, and looking at peaks on these weak lensing maps. The most massive peaks on these weak lensing maps are usually caused by galaxy clusters. And if we can find these galaxy clusters, there's a couple of advantages of this. First, because they are completely selected purely using weak lensings, the observable is directly linked to the underlying mass, and also that the selection function in the scaling relationship can be quantified by gravity alone. This gives you less uncertainty in the scaling relationship and potentially more constraining power, cosmologically speaking. And astrophysically speaking, this is just a fun sample of galaxy clusters where the selection is not depending on the baryonic physics clusters. So if you're interested in cluster evolution, you don't want to have a biased samples, then this is also interesting to look into. And most importantly, because these are weak lensing cluster cosmology that is done purely on a weak lensing catalog. This gives you a very good consistency check with other weak lensing probes, such as two-point correlation. So you can use the same weak lensing data set and get two-point correlation cosmology constraint, and can use the same weak lensing data set to get cluster cosmology constraint. And you can check the internal consistency of your data, and this can shed light into cosmological tensions, such as the SAA tensions. So today I want to demonstrate that this is possible using the super efficiency data. And to do this, as a first step, we want to do a very conservative weak lensing samples and use them to measure cosmologies. What I mean by this is we only want to select the most massive peaks on the weak lensing maps, which correspond to massive clusters, and also we have a very conservative source selections to avoid any baryonic physics that we don't understand. So for example, we want to avoid contaminations by emissions from close to other galaxies. This is the depth of these weak lensing circuits, which give us this efficiency levels one of the deepest survey on the ground. We can select source galaxy that is only on the background of our galaxy clusters, so that we do not select any massive galaxy that will include our galaxy. We also, when generating these weak lensing maps, we use a filters that is chosen to find distributions from the inner part of the halos, which is very sensitive sometimes to baryonic physics. With these in mind, we can generate weak lensing maps. Here's a cutout of weak lensing maps. When we pick on these peaks on these weak lensing maps, which typically correspond to massive clusters. So with the 3 years of HAC data, we create a 500 square degrees of weak lensing maps. And on these frequency maps, we pick out these peaks that have signal-to-noise ratio about 4 peaks. For instance, we select 129 peaks, and we find almost all of them has optical counterpart corresponding to the massive clusters. So this gives us a very large samples of galaxy clusters that are selected purely based on gravity. And this is only using 500 square degrees of frequency maps. So with things like Romans, you can have a much larger galaxy cluster sample that is interesting because they are selected purely from gravities. So how can we go about from using these galaxy cluster samples and do cosmologies? We still need to model the mass observable relationship, even though they are mostly dominant by gravity effects. What I mean by this is given a bunch of payloads that has described by some physical properties, we want to know how we can link those to the noisy frequency observable that we see. And this is important because even though it's dominant by this gravity effect, we are still trying to select things that has strong projection contamination along the line of sight, or selecting payload that is slightly truncated along the line of sight. So how do we characterize these selection effect and the scaling relationships? So what we do is we generate analytic payload profiles and project them into our multipliers. And then from this multipliers, we can make frequency maps and do a full model to select peaks on these maps. Then we connect analytic field profiles, which lead to underlying physical properties to the frequency signal-to-noise ratios. To put it into perspective, here's examples of one galaxy clusters. So we inject them into different realizations of Mach simulations, taking into account both projection effect from large-scale structures and also effects from survey geometries. And we repeat this multiple times, and we can get the distribution of frequency signal-to-noise ratio for the single clusters. And we repeat this process for ensembles of different clusters to quantify the scale versions and also the mass observable relations. So this gives us a link between the NFW-like halos to the frequency peaks, which take into account short noise, survey geometries, uncorrelated cluster structures, chance projection, etc. But of course, real world doesn't look like this. Real world look like this. So those are these conditions. We don't know what the real halos is described by NFW halos. There are things like halo triaxialities and also deviation of halo profile from NFW-like descriptions. So these are modeled by nuisance parameters that will infer further from data. So with these, let me just jump to our results. So here is 3 contours showing 3 different constraints coming from the same frequency HAC Y3 data. On the red is showing the constraint from these shear selected clusters. You can see there is a strong degeneracy between sigma 8 and omega matters, because for now, for these clusters, we do not use any redshift information from it. Redshift information requires further follow-up through optical surveys, which there is further complications that we are currently working on. But right now, this is just weak-lensing peaks with only signal-to-noise ratio as the only observables. So this gives us a constraint that looks like this. Immediately, you can see that these 3 contours are coming from the same data sets. So this is a good consistency check to see if your data set is self-consistent. And the other thing, you can see the degeneracy direction for these different contours are slightly different from each other. So if your data is internally consistent, by joining these contours, you will get stronger constraint just by introducing extra cosmological probes. So for example, when we talk about SA, we are typically measuring the contour with perpendicular to this degeneracy directions. And for our weak-lensing selected clusters, the degeneracy direction is slightly different. So by combining these 2, you can get stronger constraints. So how do our results stack up against all these other probes? What we find is our data is consistent with most other cluster probes, and are also consistent with Planck, given the limited statistical power we have. And it's also consistent with HAC cosmic shear only probes. But once we add in correlation functions, the 3x2 point correlation function from HAC alone, which is the same data set, shows slight tensions with cluster probe from the same weak-lensing data. So this is something interesting that tells us potentially something is going on in our data set. And what can we do moving forward? One of the major things is we want to break the degeneracy between omega matter and sigma 8 by introducing redshift information. So here is an end-to-end forecast using 1,000 square degree HAC-like mark. The blue is what we are currently doing without any redshift information, and the red is only introducing 3 coarse redshift bins. And you can see that you immediately gain some degeneracy breaking powers on sigma and omega matters, and you start to constrain dynamical properties such as the dark energy equation of state. And in the future, with Roman data, you have both wider and deeper data, so you can further tighten these constraints. So to summarize, I hope I demonstrate that with current data, we can already start to see cosmological potentials using galaxy cluster sample that is constructed purely from weak lensing data. This is interesting both cosmologically and astrophysically because it gives you very different selections of these galaxy clusters. And by combining with 3.2-point correlation functions, either shed light into potential sigma A tensions, but can also tighten your cosmological constraints. And I look forward to applying these methodology to Roman data in the future. Thank you.
So we have a lot of hands up. Just a quick reminder, before you ask questions, please tell us who you are. Okay. How about Matt first?
Sure. Hi, Matt from Columbia. Very well presented. The one thing is that when you're putting the cluster profiles in the simulation boxes, do you do any preferential selection to where they sit in the simulation box?
We don't for now. So these are random simulations. So it's only taking into account uncorrelated structures. So it is not taking into correlated or clustering. So this is indeed something that is a potential error in our modeling part. But for the current statistical powers, I think we're not yet sensitive to this.
Yeah, perhaps when you start including redshift, that would pose more of a problem. Yes. Thank you.
Yes.
And Koekstra, universally, I know you're in a cluster session, but it strikes me as you're just doing peak statistics.
That's right.
Why are you going all the route to clusters? Because you can do peak statistics. And actually, we did some recent work where if you then assign a redshift to the peak, you actually can constrain cosmology much better. So you're avoiding the whole discussion of whether you're looking at a cluster or not. You just look at the peak and you assign a redshift. So
exactly. So this is essentially peak statistics, but in the sense that we only look at very high end tails of the peak statistics, which link back to cluster cosmology. And I think typically for like a signal to noise ratio of 3 peaks, you use like kind of a fast forward modeling method to like simulation inference method to infer cosmology. Here we're using an even simpler framework, which just use a halo mass functions to describe these most massive peak.
Yes, but you still you could have gone straight to the n-body simulation.
That is correct. Yes. There are some tricks where we do here in terms of these injection simulations where we actually don't need to perform a lot of n-body simulations. So this is something like that is quick. But indeed, if you have a full simulation pipelines, then we can go, like right now we throw away a lot of information by not including these intermediate signal to noise ratio peak. But we kind of do this as a demonstration of just with the end tail of these peak distribution functions, you can still get some cosmological constraints. And I think things get slightly more complicated. I think the systematic effects become slightly more complicated once you include less significant peak.
No, I'm not saying you have to go to lower significance, but the point is that the mass function is based on an n-body simulation that you could have just created a
Yes, correct. Yes. So I think we choose this way just for computational sakes, but indeed, if we can also go that way too. And happy to discuss more.
Sounds like we are going to have a discussion during the reception. But for now, how about we move to the question in the back?
Hi, Nihongo OSU. Have you thought about increasing, or can you talk about going beyond peaks maybe, and how to increase number counts from shear maps of clusters? Is there ideas of using a match filter or something to boost number counts of clusters or something like that?
Yeah, so this is another thing that we're thinking about. So typically for SC, you have multiple match filters and you use that to maximize selections of halos. So here we use only a single filters as the first steps. And indeed, that's something that we can explore further by using different kind of filters to maximize our selections of peaks on these weak lensing maps.
Did we also have a question from this part of the room? Okay.
That was me. Matt asked my exact question.
Oh, okay, great, awesome. I think it is time for us to move on, but let's thank the speaker again. So our next speaker is going to be Andrea Salcedo, postdoc at the University of Arizona.
Can you please put the lapel mic on, please?
Lapel mic? Yes, you can. Lapel mic would be great.
Does it work? It works? Okay, good. Sorry, I had to make sure I knew how to use this. Hello, everyone. Thank you for the introduction. Luckily, Tomomi gave most of the background and motivation for this work, so I'll just go straight to something that I think is very cool. So here you can see constraints on omega m and sigma 8 from Planck in the black and DES year 1 3x2 in the green. So everything looks reasonable. These two probes are in rough agreement with each other with perhaps a hint of attention in S8, right? Here is what you get when you do the same, or here's what you get when you do an analysis on the same imaging, but instead for red mapper selected clusters. So this is the DES year 1 cluster analysis using a standard approach which explicitly parameterizes a mass observable relation and then uses halo model type calculations to predict their lensing abundance. And you can see that that's in very strong tension with both Planck and 3x2, even the same exact imaging, which is driven mostly by a preference for low omega m. So when these results were produced, basically people immediately determined that they were implausible and most likely due to a misspecification in the modeling of the selection of the low richness clusters. And so this motivated us to develop our own approach to cluster cosmology that forward models that selection. And so that's what we get when we use our approach. And so we have shifted in the direction of 3x2 to higher omega m into consistency with the other DES probe. We're still in some tension with Planck, but things seem at least reasonable. And we've also significantly improved in statistical precision. So I want to next show you what we expect to get in Roman. Now, of course, our constraints in omega m and sigma 8 are also much improved compared to DES. But I think more interesting is this, showing the constraints on dynamical dark energy. So this is a forecast using our methodology for the Roman medium tier survey assumptions. And so you can see that our red contour there is very small, even relative to DESI plus Planck plus supernova. So we're very excited about this. So next I will try to describe how we accomplish this. So our approach basically consists of attempting to forward model the selection of the galaxy clusters. So the first step in doing that is to generate a mock galaxy catalog, in this case with a HOD-based approach. And so the idea here is that you're generating the galaxies that are candidates for membership in those clusters. Then, based on the literature, we know that a count cylinder process more or less approximates the cluster optical selection algorithm. So we do the same thing in our simulation. We assign what we call n-sil to each halo based on the number of galaxies that are within some cylinder centered on that halo. The aperture and the depth of that cylinder have something to do with the selection algorithm applied to the data. And then we select clusters based on abundance matching to the richness. So this n-sil quantity is not assumed to be identical to the richness, but we assume that it has some tight correlation with the richness such that the ranking allows us to do this abundance matching. And then you can compute the cluster lensing, which in this case means you just cross-correlate with the simulation particles. So just another word on this abundance definition of the bins. So again, we're not assuming that the richness is identical to this n-sil quantity that we compute, but we're only assuming that the ranking of n-sil very closely approximates the ranking of richness. This relaxes our modeling requirements and allows us to do this selection. And so here I can just take you through exactly what we're doing. So in the data you have richness indicated by lambda, a richness bin that you use to select a cluster sample. So here I'm plotting that against the cluster density. This richness bin defines a bin in cluster abundance, and you can sort of transform that bin in cluster abundance into a bin in n-sil. And so that's what we're doing. Okay. So you might ask whether or not this produces consistent results or if you lose information from throwing out the information coming from counts. So here this is addressing this question. So we've done mock tests on clusters identified in Flamingo. This is work by my collaborator Heidi Wu. And so here I'm showing you the fully marginalized constraints on omega m and sigma 8 from 3 tests. So what we call match n-sil is referring to the traditional way of just explicitly defining richness bins. And so you can see that if we use just the lensing in that case, we get basically no constraint. You need to include the counts plus the lensing. That's the green. The red is our abundance matching method. And so we're happy that we're in basically complete consistency. We're not biased with respect to the traditional method, and we have more or less the same precision. Okay, so everything that I just described to you takes roughly 20 to 30 minutes to evaluate on a single simulation, so single HOD for the member galaxies in a single cosmology. So to do inference rather, we have to come up with some interpolation scheme to speed this up. So we do Gaussian process emulation. It works, so we don't need to do anything more complicated. Here on the left-hand side, I'm showing you our training set relative to the DES year 1 data. That's in error bar, points with error bars relative to the lines. And so you can see that our training set spans the data very nicely. On the right-hand side, I'm just showing you the leave one out accuracy as a function of RP and then also richness bin. So we're achieving roughly 3% accuracy at all scales, which is sufficient for DES year 1. So this is fast and accurate. That process that takes 25 to 30 minutes takes roughly 1 second when you do this. So we come back to the cosmological constraints. So again, here on the left-hand side, we have our constraints in red relative to the initial analysis using the standard approach in blue. We have resolved this tension and produced much tighter constraints. And so part of this comes from the fact that we are basically accessing all the information, all the full shape information and lensing profiles. And another part of it is that our methodology allows us to go to much lower richness. So here, this is just showing the lensing profile as a function of cluster-centric distance for the data in points and error bars and our best fitting model in the lines. And so you can see that we have a good fit all the way down to low richness. So purple and brown are richness 14 to 20 and 10 to 14. Okay, so we've also, of course, done systematics tests to convince ourselves that this is not crazy. Here are 3 such tests. So on the left-hand side, we have constraints coming from 3 tests where we split the sample by richness. So we looked at the constraints that are coming from the lowest richness pair of bins, the intermediate pair, and the highest pair. On the middle, we have similar constraints coming from individual redshift runs. And then the right-hand side, which I think is probably the most interesting, are constraints coming from what we call large or small scales. So in all cases, there's no internal bias within the data vector. So we are happy to say that everything looks robust and we trust our constraints. And as far as the right-hand side is concerned, this also shows that our treatment of the baryons, which I won't go into too much detail, seems to be working just fine. So preparing for Roman, what I've shown you thus far has just showed that we have this cylinder-based model. We think it can describe the cluster lensing data down to low richness and produce competitive and robust cosmological constraints. So there are 2 main drawbacks of this. The first is that we cannot currently explicitly model the richness, hence the need for this abundance matching. And we also cannot do cross correlations with the galaxies. So our solution is to generate mock galaxy catalogs with the necessary imaging so that we can run RedMapper directly on those catalogs. That explicitly produces richness as RedMapper sees it, right? And then also we can run red matching on those same catalogs and then do all the cross correlations, 3x2, et cetera. So this is work that's being led by Keenan. He's a University of Arizona junior. And so what he's doing is he's taking an Abacus Summit light cone, populating with HODs. He's assigning Z-band magnitudes using a Schechter function. And then he's able to take the red sequence model that RedMapper produces itself. So when RedMapper runs on the data, it produces a model of the colors versus Z-band magnitude. And so he can use that to assign the colors to his mock. Then he can run RedMapper on the resulting catalog. Parentheses, he can also run RedMagic. On the right-hand side, this is just showing the result of one of his tests. So in the near term, we want to do this for validation of our methodology. In the longer term, we want to speed this up through some kind of emulation as well and do inference with this full forward modeling. So returning to our constraints from Roman, these are forecast constraints for the medium tier survey assumptions, so 2,400 square degrees with 40 sources per arc minute. And you can see that, I've listed the constraints in sigma 8 on omega m, but again, focusing on the constraints in the dynamical dark energy parameter space, you see that we actually have a significant improvement relative to just BAO plus CMB, and even a mild improvement relative to those 2 plus the supernova. So this is very exciting. If we're able to achieve this, we'll either be able to confirm the detection of dynamical dark energy from DESI, or if they disagree, that'd be sad, but also interesting. So I think I'm probably good on time, so I'll just leave this as a summary. Take questions.
Lord. Yes.
I think I'm almost there, but can you just fill in for me why this counts in cylinders technique A works better than richness? I think I have an idea, but B, also why you can't combine this counts in cylinders with normal 3x2 measurements in a cosmological inference.
Okay, so I would say, so why does it work better than richness? It's just that it approximates the richness selection. So if you're wondering why basically why the red is producing tighter constraints than the standard approach, I would say that that's a combination of going to lower richness clusters and also being able to use the projection effect as information that you can basically break degeneracies with. And then the second part of your question, sorry, why can you not do the cross correlations, right? That's just because, you know, in this picture, right, these red galaxies, which are somewhat of an abstraction to do this selection, those should be correlated with the galaxies that you would be doing the cross correlation with, and we just don't know how to handle that essentially. So if you imagine that you would be looking at red mapper selected clusters and then cross correlating with red magic galaxies, some of those should be red magic galaxies, right? And we don't know how to model that cross correlation. But if we do the full forward modeling, then, you know, going from the colors, right, then the algorithms themselves will, by construction, produce that correlation.
Yeah, thanks for the nice talk. Can you say more about how the aperture and length of the cylinder are optimized? And is that length, is it redshift dependent?
Yeah, so we don't have a lot of sensitivity to the depth. So we've run tests where we let it be free and then we fix it in our fiducial case. The value that we fix it to is based off of the lambda of z method for calculating the projection, the width of the projection kernel, and so those measurements are redshift dependent. Yeah.
Ooh, finally. Any more questions in the room? Do we have questions online? Okay. Oh, yes.
Yes. Matt was in Columbia. Just, is there a configuration that you've tried that recovers the same results as the richness bins? Like, if you, like, let's say, exclude the low richness systems, or you make the length of the cylinder small.
Are you referring to this blue thing?
Yeah.
So I would say the main difference here is not the abundance matching. But if we run, this has been a while, but if we run a test where so if we do two tests, sorry, okay. If we generate a mock using our approach and then run the kind of standard halo model calculations, we can produce a contour that's off in the correct location. Actually, it's at high sigma 8 as well, because this is the analysis that was after unblinding, right? So the original blinded approach was up at high sigma 8 as well. So we can reproduce that. We can also, if we try to fit the DSY1 cluster lensing with the mass observable based model, we also cannot get a good fit, which is another feature of this result. Yeah.
So the timer did beep, so we need to move on. Let's speaker again. Oh, okay. So the next speaker is gonna be Kyle Fenner. It's gonna be virtual online. Kyle?
Hi, can you hear me?
Whenever you're ready, can you start sharing the screen?
Okay, can you see my screen and can you hear me?
Yes, works well. Thank you.
All right. Sorry.
Great to start at the time.
Okay, thank you. So I'm Kyle. I'm a staff scientist at IPAC at Caltech, and today I'd like to share with you how to utilize Roman to study the onset of galaxy clusters with gravitational lensing. And by onset, I mean basically from redshift 1 to redshift 2 or so. So I start out here with a quick description of galaxy clusters. Springlet all showed in the Millennium simulation that they're at the nodes of the large-scale structure. And by mass, they're about 85% dark matter, 20% ICM, and 1% of that stars in masses in stars. And those stars are in galaxies as well as in the intercluster light. And the question I'd like to study is, how do all these components evolve in unison? And here I show two clusters that are basically on the opposite ends of the spectrum of merging clusters. We have on the left a relaxed cluster that is spherical looking from this Chandra image that's giving us the X-ray emission. And then on the right side of this is the famous bullet cluster, which is highly disturbed, shows ram pressure stripping. Now here I show another cluster. This is PLC-KG 287 plus 32.9, and it's also a merging galaxy cluster. Now, clusters accrete matter from the surrounding large-scale structure, and this accretion drives turbulence into the ICM. Then charged particles are stochastically accelerated in the magnetic structures of the turbulent plasma, leading to a radio halo. And so this is the X-ray emission for PLC-KG 287, and if I go to the next slide, we have the synchrotron emission, the radio emission. We have the radio halo in the center, which is tracing the X-ray emission. And then in rare occasions, we get the most energetic events that occur in the universe, which are when clusters collide. And these clusters collide at supersonic velocities, which form shocks in the ICM. And then charged particles are also accelerated in the magnetic fields of these shocks, which are forming radio relics, as shown in the bottom and here with blue arrows. These are the radio relics or shocks. So these processes that are the result of accretion lead to all of these observable effects that can tell us about the growth of galaxy clusters. And then to study the dark matter, the most massive component, we can use weak gravitational lensing. And we've already had a bunch of weak lensing talks that are focused on cosmology. Mine's more focused on the astrophysics of clusters. But weak lensing uses the shapes of the background galaxies to infer the cluster mass distribution. And the bullet cluster is an amazing example of this. So here in this nice image created for us, we have the mass distribution from weak lensing shown in blue colors, and then the Chandra X-ray emission in red. And you can clearly see the ram pressure stripping of the bullet from the mass distribution. And this is from a paper of Cha et al. That we published just a few weeks ago. And so I've actually done a study of many nearby clusters out to redshift 0.54, looking at those with radio relics or shock waves in them. And here are 8 maps showing the X-ray emission from XMM or Chandra, plus the radio relics from various radio telescopes. And this is just a small subsample of those that are published in Finardal 2025. We did a weak lensing analysis of them and mapped the projected mass distribution. And then we combine that, we estimate masses of these subclusters as well, and then combine that with the information of the X-ray and radio to try to understand how the cluster mergers unfolded, because we only really get this one time snapshot per cluster of the merging scenario. And then another step we take is we compare these observed clusters to simulations. And so on the left, we have Able 1240, which has 2 radio relics at opposing ends of the elongated X-ray distribution. And we have the weak lensing mass map with 2 peaks. And on the right, we have a cluster from the TNG cluster simulation. This is in Lead 2025. And they've mapped out the X-ray emission, the radio emission here in the green contours and the X-ray emission in the purple and yellow, and weak lensing or mass density contours are the white. So by utilizing simulations, we can try to understand the past history of these types of very energetic cluster mergers. And then we can do statistics on them as well. So here we took the primary and secondary halo in the collision that formed the shock waves, and we see that most of them are in a major merger, so the mass ratio less than 4:1. And then comparing weak lensing mass estimates for each subcluster to the velocity dispersion mass estimates, we can see that there's a slightly elevated velocity dispersion, which may be from the energy of the collision. And then on the right plot, I show the luminosity, or sorry, a luminous tracer of the mass peaks. So the BCG is in blue for each subcluster. The number density peak is in green, and the luminosity density peak of the galaxies is in red. And we find that the BCG better traces the dark matter peak. But that's all at low redshift. And what we really want to do is move this up to high redshift, where clusters are just starting to form. And the SZ surveys have done an amazing job at starting to detect galaxy clusters at high redshift, above redshift 1. Here's a lot of the SZ detections from the past couple of years. You can see there are many clusters up above redshift 1 now. And there's also the E Rosita clusters that are being detected at lower masses towards the left side of the plot. And recently, we started to detect radio halos at high redshift using the amazing radio telescopes like LOFAR and Meerkat. So here's a radio halo at redshift 1.34, which suggests that magnetic fields are forming very early in these galaxy clusters. And we would like to study these with weak lensing so we can look at where the dark matter is distributed in them. However, from the ground, this is very hard because you have the atmospheric blurring, which makes a large PSF. And you also have source confusion, which leads to a very low number density of background galaxies, typically about 30 per arc minute squared. With space telescopes, we have a much smaller PSF and it's more stable. And the higher resolution leads to less source confusion or less blending of galaxies. So I asked the question here, what is the ideal telescope for weak lensing analysis of redshift greater than 1? Now, we've already done this with Hubble. On the left figure, I show some of the major weak lensing surveys that have been done of the universe. And you can see that there's quite a few below redshift 0.6 that have been done from the ground. And then above that, we have really 2 that have been done with the HST ACS instrument, G et al. In 2011 and Schreibeck et al. In 2017 or 18. And here are 2 examples, one from each of the high redshift surveys. In the center panel is a cluster from Schreibeck et al. That appears to be a merging cluster because it has BCGs on opposing ends of the X-ray peak, kind of like the bullet cluster. And the mass map kind of leaves a lot wondering because it's a very spherical distribution. So there's a lack of detail that you can achieve with HST ACS at redshift of 0.8. On the right is a cluster at redshift 1.23. And we have a detection of the mass peak that is in agreement with the X-ray peak, which is the green X in the center, but there's really not a great correlation between the cluster member galaxies shown as red circles and the mass distribution. So this is more of a noisy result for the mass. And where we'd like to get to is JWST gravitational lensing. So this is Able 2744 on the left, it's a nearby cluster, and the bullet cluster on the right. And with JWST, you get so many background galaxies, you can create a very high resolution mass map. And in these 2 cases, the mass really well traces the galaxy light. But I'm kind of cheating here because these both include strong lensing, which really ties the mass peaks to the bright cluster galaxies. However, JWST is a small field of view, and so is Hubble. So here's R200 of Able 2744. The bright galaxies we were looking at are in the center of the cluster here. And then if we overlay the JWST imaging, you can see it's very small compared to the R200, the virial radius of the cluster. So with Roman, we'll be able to do a much better job of probing the full size of galaxy clusters. And that's what I'm showing in the bottom right here. If we look at the bottom curve, it's about a 10 to the 14 solar mass halo as a function of redshift, and JWST can barely capture that even out at redshift 2, but Roman can easily capture it and allow us to study the full distribution. And this is very important for merging clusters where they're much wider distributed. And here's the the Roman field of view over that field. Going to infrared has a lot of advantages for weak lensing. In Lee et al., they showed that the number density of galaxies in the infrared are about 1.5 times higher than in optical, which gives us a lot more for the statistics of weak lensing. And also the light profile in the near eye is better fit with a smooth model. Whereas if you're looking at the optical light, it's very clumpy. So Roman has some advantages over HST. It has a larger field of view, a better sample PSF, more stable PSF, and redder filters. And so last year when I presented, I was asked a question, should we do wide field surveys to study these clusters, or should it be pointed observations? And wide field surveys, like the High Latitude Wide Area Survey, have a lot of advantages. There's lots of overdensities in a large variety. There's shear selected instead of red sequence or ICM emission, which gives us different objects to look at. And we can detect low mass overdensities that are X-ray faint. It also gives a very good sample of the average galaxy cluster. And so I put two figures here. One's from a paper that I'm preparing on the Candles Cosmos. It actually includes all the Candles fields, but this is the Cosmos here, detecting very low mass weak lensing overdensities, around 10 to the 13. And on the right is the Dark Energy Survey science verification overdensities. But this type of thing lacks rare objects, so that's a disadvantage. And I'm just going to finish by showing you a rare object. So this is XLSSC 122. I had a redshift of 2. And so we got JWST data on this cluster and detected the peak of the cluster very significantly. And this is something that would be missed in the high latitude area survey because you need pretty deep data to detect it, about 29th magnitude depth to have a robust detection of the weak lensing mat. And then if you want to get the distribution of the matter to look at substructure, you really need deep data. So I'll just put my conclusions up here and thank you.
Thank you for being on time. Any questions from the room? Any questions online? All right. So I could ask a question. So you showed that a GWST, the mass distribution. Do you how well does the GWST derived result from compares to other previous results if you have the same mass measurements for the same cluster?
So the number density of galaxies is much higher. So for Hubble ACS, we typically would get about 50 galaxies per arc meter squared, and with JWST we're achieving around 350. So we have a large increase, a much better mass estimate from it. We can better discern subclusters using the JWST, and the uncertainty on the mass estimates are typically about 10% with that kind of statistics.
Wow, that's really nice. Thank you. Yes. I'm not sure if Kyle can hear you though, so I'm gonna pass you the.
Kyle, can you hear me?
Yes.
Oh, okay. I think there are mics around. Especially for these low signal to noise, really high redshift clusters like this very cool example here. How do you go about finding targets for potential follow-up, especially if the signal to noise is below the shear selection threshold for something like Roman? Do you just get lucky?
Oh, I think the easiest way is to rely on the SZ telescopes to detect them first and then to study them or to do follow-up observations or hope that they're in the large survey footprint. When it comes to detecting them from a shear selected sample, I think it gets very hard because you're down into the 2 or less than 3 sigma detection. And I guess you could do a lower cut on your shear selection and then look at other observables to see if it's a bonafide cluster, like look at the red sequence or search in the X-ray data.
But it seems like an SZ search to get an initial list of targets is the best way to go.
Yeah, I think so.
Thank you.
All right. Thank you very much, Kyle. Let's thank Kyle again. So the next part of this session is going to be poster pop. So we actually have 16 speakers for this part of the session. If you could all come to this side of the room and we'll get the slide set up for you.
Oh my God, this is going to be interesting. Who's the first? First volunteer. Nandi.
Right.
Okay, you are here.
It's actually going to be the other one.
Just come here in the middle and talk.
Do you want to just maybe stay?
No, actually, this is not the version that she downloaded. Yeah.
Oh gosh. Really? Where was this? On the box, probably.
Yeah, this is. No, if you can just go back.
Oops, sorry.
Seems like a good idea.
I think it's better.
Yeah, it's this one. So can I?
Yeah, you can download. Voilà. And this means props. That's all. Okay. Sorry.
Hi everyone. I am Gaurav Nandi from University of Missouri, Columbia, and my poster is about near-infrared size evolution of dwarf quiescent galaxies up to redshift 4. So we use deep JWST imaging from JETS and CS surveys to model over 60,000 dwarf galaxies with tools like GalFit to extract the stellar size and easy to obtain the stellar mass, rest frame colors, and photometric redshifts. And by fitting the stellar size mass relation with MCMC, we find that star forming as well as massive quiescent galaxies grow significantly bigger with time, whereas their lower mass counterparts remain compact as if they are frozen in size, suggesting a different evolutionary track, possibly tied to environmental quenching mechanism. Having that said, looking ahead, we plan to leverage Roman's wide field imaging to trace more such low mass galaxies over large sky area and diverse environment, from dense cluster to isolated fields, to better understand how such large scale structures quench star formation and shape the evolution of dwarf galaxies. So if you want to learn more about my work, feel free to come and stop by my poster set up at the cafe. Thank you.
Yeah, I know you. Where is this thing?
Number 2.
Yes, you're number 2, but it's.
I was number 2 on this.
Oh God! Now we lost the thing. Sorry, I lost the list.
Farther down the list and the.
Otherwise, we open everything from there.
Yes, down.
Yes, down. Where are you, Lucas? Oh, thank you.
Yeah. Okay. Hi, I'm Ray Lucas, staff scientist here at Space Telescope. This is not my entire poster. This is the poster pop version of the poster, but the entire poster is very similar to this. Before I say any of that anymore, though, I want to say a quick word. I may be one of the few people in this audience who actually had chances to interact with Vera Rubin and Nancy Grace Roman. I used to sit in this auditorium with Nancy Grace Roman before I knew who she was. sitting back there knitting and then suddenly asking really piercing questions about the development of HST. But I learned eventually. So it's nice to see them honored with these telescopes we're talking about. So the main purpose of my poster is really just sort of an advertisement and an admonition, but I don't feel like I need to do the second part too much. There have been lots of presentations of really good ideas and things to do. I wanted to highlight one JWST program that I'm part of. It's called Venus. It's an acronym. It's not about the planet Venus. It's 60 massive lensing galaxy clusters that we got time to observe with JWST. Our focus will be on the lensed objects and the clusters themselves. But the half shell part about this title here is that everything lives in an environment. And clusters, as they evolve, of course, influence their environment and are influenced by their environment. So I just wanted to urge people to think as much as they can about that kind of aspect. The combination of Rubin and Rubin, optical and infrared for lower redshift to higher redshift, rich clusters, poorer clusters, protoclusters. There's a lot that can be done in all sorts of ways with these. And even though this sample of 60 galaxies is a big nearer by thing, redshifts ranging from 0.18 to 0.97, it would be good if that kind of thing is pushed on out to higher redshift. And that's all I've got to say here. Thanks.
Peterson's video is so perfect. Thank you.
Hello, everyone. I am Eric Peterson. I am a recent postdoc at Duke University. I worked in graduate school with Dan Skolnick on supernova cosmology, specifically focusing on near-infrared supernova analysis, as well as peculiar velocity and galaxy group work. In just 3 weeks, I'm moving to Michigan. Excited about that and excited about the intergalactic dust project I'm also working on that you can come talk to me about on my poster. And I'm also giving a supernova update talk, a supernova pit update talk on Wednesday. So thank you.
Hi, everyone. I'm Jonathan Blazek from Northeastern. Other members of our team are listed up there, and I'm happy to give a short advertisement of our poster about galaxy intrinsic alignments. So you heard a little bit about this already in Agnes's talk earlier. I think there's going to be some more interesting talks later in the week. The basic idea here is you have physical correlations between galaxy shapes that can look a lot like weak lensing, even though they are not themselves weak lensing. So if you don't treat it carefully, it can bias your results. So as Agnes mentioned, this is actually one of the most important systematics we're going to have to worry about. So what we have here is just a sketch of our method to try to simulate this. So to produce accurate simulations that include intrinsic alignments. That's what this top row is, kind of going from the method of placing aligned galaxies and halos, and then to applying this to simulations to both try to reproduce what hydrosims are doing, but also to create large realistic catalogs on the light cone. And then at the bottom, we're using the same simulation techniques to actually train neural networks and use this as a direct modeling technique for IA. So come to the e-poster, come chat with me. Some papers are down in the bottom right. Very happy to chat more.
All right. Well, other than intrinsic alignment, the systematics that people worry about most for 3x2 point weak lensing studies is photometric redshifts and our understanding of redshift distributions. And to get things down to the necessary accuracy to meet requirements, we really need new spectroscopy reaching galaxies as faint as the objects you use in your lensing analyses. And so through the High Latitude Imaging Survey PIT team, along with some people from the spectroscopic survey team, we've put together a proposal, a white paper on what you can do with the PFS instrument on the Subaru telescope, which is really designed to get large spectroscopic samples, getting simultaneous spectra of more than 2,000 objects in the optical and the infrared. And so we've developed a proposal we call the Super Deep Survey, which would be the definitive photometric redshift training and calibration data set for Roman. It would obtain somewhere in the range of 10 to 30,000 spectra in total, depending on what's being done for complementary surveys. It will require a total of about 50 dark nights on Subaru. And because of the requirement that we need to be observable by Subaru and be contiguous with the High Latitude Imaging Survey to enable the precision calibration we need for PhotoZs, there's only two fields on the sky that work for this, the Cosmos field and the XMMLSS field, which are deep drilling fields for both Rubin and Roman. And so this would also be a wealth of data that would benefit things like galaxy evolution, science, as well as cosmology, hopefully appearing sometime in the next decade. So thank you.
A few more on Zoom.
Oh, sorry?
We have a few on Zoom, so do we want to start with the two to the in-person ones?
Oh, there's a visual?
Yeah.
Oh.
Just do full.
And a second one is this one, Romanowski?
Oh, yes, it's online.
Okay, so we can put it on and just.
Sorry, we have a few poster pops from online. We're going to do that after all of the in-room presentations.
Okay, so
sorry.
I didn't get it.
Should have talked about this.
That's okay, don't worry. It's easy. Now I'm getting.
All right, thank you. This is also about alignment. I'm Shenming, I'm a postdoc at SLAC. So the question I want to ask is, on average, how do clusters differ along their project major and minor axis? But we want to study this question at very large scale and just use the public data or observational data. So what we did is to stack thousands of nearly relaxed clusters and just look at their lensing signal and the galaxy density profile. And we can see the signature of traxality up to like tens or, around tens of MPC. For weak lensing, we can see things to like 40 MPC. For galaxy density, we can see up to like 10 to 20 MPC. So this is just telling us the alignment of structure inside the cluster to very, very large scale. Yeah, so that's it.
Should he?
Okay. Hi, everyone. I'm Shirley from UIUC. Today we talk about a lot about like weak lensing with Roman. So there are a lot of challenging. In one hand, we need faster pipeline. On the other hand, there's a lot of different bias from PSF, noise, and all other things. So today, our group, we want to develop a deep learning-based model that can do detection, classification, and shape measurement, PhotoZ, everything all at the same time. Like a beef can factory for weak lensing, imaging, catalog out. And for our group, we got grant, and yes, they're working on PhotoZ and deep learning, and I myself focusing on the shape measurement. And I put shape measurement module into the existing model, and I also developing like correspond augmentation to optimize the performance. And for now, we got like quite decent speed. And we are also working on using meta detection to calibrate our model. If you have any comment and want to collaborate with us, feel free to discuss with me during the cafe or shoot me some message over Slack or email. Thank you so much.
Thank you. Good afternoon. My name is Keith Buckles. I'm an undergrad at Yale University. I'm here working with the Galaxy Redshift Survey Project Infrastructure team. I'm working on incorporating a wavelength-dependent PSF into our GRISM simulations. The reason we're doing this, I hope, is made clear by this very first image in the bottom left. If you just use a single PSF when you perform this dispersion simulation, you get this very flat-looking dispersion. But if you instead use this wavelength-dependent version of things, you end up with these wings shooting off the side. It creates very different contamination, very different noise to nearby objects. The thing you can't see with your eye is if you read those pixel values along the dispersion, as things get more red, you'll see those pixel values drop as the PSF gets larger and the flux is spread over a wider area on the detector. So we want to learn to handle these properly and to account for that. So that's why we're including this in our GRISM simulations. If you would like to discuss any technical details, figure out or learn about how we did this and discuss the technical problems we still have to solve to make this an even more efficient and effective process, you can find me right after this or at coffee tomorrow. Hope to see you then.
This is it.
Hello, everyone. I'm Yash, and I'm a postbac research assistant at UIUC, and my work is also an extension of Deep Disk, but specifically focusing on deblending using joint survey data. So with these new wide field deep surveys like LSST, Euclid, and Roman, we're getting lots of new observations and lots of new data and new science, which is great. But this also exacerbates the issue of blending, specifically unrecognized blends, which is when sources are multiple sources are detected as a single source. And these are particularly problematic because they introduce systematic biases in flux measurements, redshift measurements, and they affect critical downstream cosmological analyses because a lot of typical deblenders utilize source catalog initialization. So these deblenders just pass over these hidden blends and don't actually deblend the source like we want them to. And so what we're trying to exploit is the overlapping regions of LSST data and Roman data, and specifically using Troxel's 2023 high latitude imaging survey simulation coads, which has 20 square degrees of overlap with LSST's desk DC2 images. And so traditional methods also for unrecognized blends essentially use anomaly detection after the catalog has been created. But what we're trying to do and what Deep Disk is essentially doing is more of a preventative approach and being able to use deep learning instant segmentation to be able to identify, deblend, and classify and detect sources before with just the raw pixels rather than creating a whole catalog. And so with the power of Deep Disk and joint survey processing, we're hoping working on creating a better detection catalog that's really fast and reducing the number of unrecognized blends in our actual catalog and being able to make more robust cosmological analysis, which will better help our constraints which will better help constrain our cosmological parameters. Thank you.
Next is sorry.
Hi, everybody. I'm Grant Burrs. I'm a graduate student at UIUC, so I'm also in this Deep Disk group. As my collaborators have described, kind of this holistic machine learning framework designed to just produce object catalogs directly from survey images. And so my work has been on adding photometric redshift estimation capabilities to this framework. And so I've done this by adding a PhotoZ module to the baseline network that not only produces PhotoZ point estimates, but also uncertainties, which can then be used in Bayesian analyses. And so the network has been trained, tested, and validated on some simulated LSST data and compared to other sort of traditional PhotoZ codes. Also currently working on applying this to some JWST data and also some simulated Roman data. So I have an e-poster. Come and talk to me if you have any questions or comments.
Hi, everybody. My name's Catherine. I'm a grad student based at Ohio State. And my poster is about MD-Stripe, which is a new module that we're going to integrate into the shear and clustering measurement pipeline for the HLIS that is supposed to remove stripes of noise that are present in the Roman images. So on the screen, on the left panel there, you see these noise stripes that appear on the Roman detectors. And then on the right, you see after application of MD-Stripe, which pulls out those stripes that will allow us to get more precise measurements of shapes for weak lensing. So if you're interested in how this works or generally interested in systematic errors on weak lensing, please come talk to me.
So you're Leidig, okay.
Hi all, my name is Katya Leidig. I'm a PhD candidate at the University of Maryland. The poster I brought this week is about using the BCG stellar outskirts as a tracer for halo mass and how it's better than using the total stellar mass of a BCG. Particularly, this is Mach observed in illustrious TNG and is forward modeling for wide field stellar halos such as with Roman. The one plot here you can look at closer in my physical poster, but it is the scatter in the stellar halo mass relationship for a bunch of different definitions of outskirt halo mass. So yeah, talk to me if you want to learn more. Thanks.
Okay, I got you.
Hi everyone, I'm Rosie Bartlett. I'm from the Liverpool John Moores University over in the UK. And at the moment I'm presenting a poster based on my work to use machine learning to localize streams in images of other galaxies. So the model we use is called a UNet. It's a little bit similar to a classic CNN, but instead of providing one label per image, it provides one label per pixel in an image. Just add it to the list. And that allows us to localize an object in the image and kind of create a cutout of the part that we're interested in. In order to do that, we need to train on similar images, so a binary mask of pixel labels for the image. This is hard to do with observational data, so at the moment we're using Auriga simulation data to construct that data set. And it's a little bit of a work in progress, so that's about where I am at the moment, and I'm super excited to start training the machine learning model. If anyone has questions, comments, thoughts, please come and talk to me. I'll be around.
So 3 more speakers.
Romanowski?
Do we have Aaron online? Oh, yes, go ahead.
Hi, my name is Aaron Romanowski. I'm at San Jose State. A poster is about near universe cosmology projects. And our team is mainly working on this survey with the Euclid telescope of low redshift dwarf galaxies and their star cluster systems. So you can think of this as sort of a preview of the type of work you can do in this area with Roman. And there's 4 different projects on the poster. I just have time to mention one of them, which is a nearby ultra diffuse galaxy. It's an interesting type of low surface brightness galaxy. And here with the image with Euclid, you can see not only could you make out some of the low surface brightness features, but resolve globular clusters candidates. This is a distance of about 50 megaparsec. And one of the key aspects is that you get a lot of synergy by combining this space-based imaging with ground-based spectroscopy and with Rubin, wider baseline photometry to get stellar populations, better distance constraints, and better constraints on the globular cluster system. So I'd encourage you to look at the other projects and get in touch if you have any questions or comments. Thank you.
So next we have Seppo, if you are online.
Yeah, hi, I'm Seppo Laine from Caltech IPAC, and our poster is on stellar streams that we hope to observe with Roman and also study in other large surveys. And from a stellar streams, these are really in integrated light and they are unresolved. So we hope to learn about mass assembly rate of galaxies, stellar population properties like metallicities and ages, the growth of stellar halos, the orbits of satellites, and the resilience of stellar disks to satellite bombardment, and maybe the other way around. So how satellites are disrupted by in minor mergers. So we have started this project, and we have published a paper on a stellar stream legacy survey using DESI imaging data. And there are examples in the lower left here of galaxies from observations, and then they can be compared to simulations which are shown in middle frame. We have also done a case study of stellar stream in SPRC 047. And it's so faint that we basically concluded that to get reliable estimates for stellar population ages and metallicities, you need large wavelength coverage from UV to mid-infrared and really high signal-to-noise data. Also, there's going to be a pipeline optimized for low surface brightness imaging called Rosalia, which takes or tries to mitigate the effects of scattered light, PSF wings, zodiacal light, and thermal emission. So I will have a poster in Slack, so please come and see.
So last but not the least, we have Yanhui Yang.
She's not here. Oh.
Yes. Can I share my screen?
Sure.
Yeah, go ahead.
Okay, thank you. Oh. Yeah. Oh, sorry, I can't share. I can't share my screen. Can you open my poster prop in your computer? It's the second.
It's in the box. Or...
Did you upload it online?
Yes. Yeah. It's.
Somewhere in the box.
It's in the second session poster prop. Yeah.
Oh yes, it's in the second session.
Okay, so you have to go stop. Speak.
Yes, the last one.
This one. Okay, that's the problem. Good, perfect. Probably have to download this stuff. Just like that.
Go ahead.
Yeah. Okay. Hi everyone. My name is Yan Hui. I'm a graduate student from UC Riverside, and my poster presentation is about making theoretical predictions for next generation surveys like the Roman Space Telescope. We have performed the Goku simulation suite that covers 10 cosmological parameters, including dynamical dark energy and massive neutrinos. And we developed T2MUs, which is a multi-fidelity emulation framework that can be used to build neural network emulators. And using this approach, we have constructed Goku-NEMU, which is currently the most powerful emulator for the nonlinear metapod spectrum with percent level accuracy, unprecedentedly high dimensional parameter space, and its broad prior range make it the only emulator that can be used to test recent DESI and DES constraints on dynamical dark energy down to nonlinear scales. And it is also the fastest emulator. It would only take about 2 milliseconds to make a prediction for a single cosmology. That's it. I can't be in person today because my flight is delayed, but I will be there tomorrow. So please talk to me if you are interested in this work. Thank you.
Oh, thank you. I think that's probably the record for the most speakers in a session. So how about we thank all of the speakers in this session again. And can I also suggest one more round of applause for our Dario here that helped us get through the session. Thank you very much. All right, we're almost on time. Right now we have the reception, right? And it's in the cafe. And please also remember to check out the posters. Thank you.
Thank you.